Imagine you're having this really deep, engaging conversation with a highly intelligent AI. Dialogue is just flowing, the responses are razor sharp, and for a minute you sort of actually forget you're talking to a machine.
Right. It feels totally natural.
Exactly. And then you ask a question, and the AI just pauses for like 1 second too long. In that single, drawn-out second of dead air, the whole illusion just shatters.
Yeah, the magic just vanishes.
It really does. You're jarringly reminded that you're just, waiting for a computer to process code.
I mean, the slight hesitation is basically the enemy here. When you're building a system that attempts to mimic human conversational rhythm, latency isn't just some technical metric. It is the entire user experience.
Right.
You cross a certain millisecond threshold, and the human brain subconsciously just rejects the interaction as unnatural. It's like an uncanny valley for audio.
Yeah, that's a great way to put it. Well, today we are looking at your blueprint to make absolutely sure that illusion never shatters. It is Friday, July 10th, 2026, and we are jumping into a custom, highly technical deep dive tailored specifically for you.
And it is a really exciting project.
Oh, for sure. You are building a massive project, a real-time streaming conversational AI platform, and you've handed us your architecture sandbox notes, specifically Section 5, Architectural Building Blocks for Scalable Systems.
Right.
And looking at these notes, the stakes of your project are defined by one absolute non-negotiable constraint, which is a latency budget of under 800 milliseconds.
Under 800 milliseconds, yeah. I mean, every single piece of physical infrastructure we're going to discuss today exists for one unified purpose, and that's protecting that 800 millisecond budget at all costs.
It's a tight window.
It is incredibly tight. We're taking these pristine, perfect theoretical diagrams from a whiteboard and translating them into, physical realities where fiber optic cables get severed, servers overheat, and network congestion just spikes unpredictably.
Yeah, the real world is messy.
Exactly. Building globally scalable distributed systems is entirely about anticipating that chaos and engineering pathways that just bypass it in real time.
Okay, let's unpack this, because making the leap from theoretical architecture into physical infrastructure is just daunting. I mean, we have this complex web of AI logic, but before your platform can process even a single syllable of spoken audio, we have to actually physically connect the user to your system.
Right, the front door.
Yeah, we have to somehow hide this massive, sprawling global network behind just one simple, clean web address.
And this brings up a really core concept in your notes, which is the single server abstraction philosophy.
The single server abstraction.
Right. When your user types in your domain or opens your app, they should feel like they're connecting to one incredibly fast, perfectly reliable supercomputer. They shouldn't know or care, really, that your backend is actually composed of thousands of independent microservices distributed across multiple continents.
They just want it to work.
Exactly. But to create that illusion, we have to engineer a flawless front door. And that starts with the routing layer.
Right, the routing layer. And reading through your notes, there's this massive red flag regarding basic DNS, the domain name system.
Oh yeah, huge red flag.
It essentially says that relying solely on basic DNS to handle your front door load balancing is just a recipe for complete disaster. Which is wild to think about, considering DNS is literally the backbone of the internet, right?
It is, but it's flawed for this kind of work.
Yeah, the notes highlight some severe, fatal flaws with how it routes traffic. It uses something called blind round-robin routing.
Yeah, it's entirely blind. I mean, when a user requests an IP address, basic DNS just hands out addresses from a list in a loop. It has no mechanism for active health monitoring whatsoever.
Wait, really? None?
None. It doesn't know if the server it just directed your user to is healthy, overloaded, or like literally on fire. It'll happily just send your users straight into a dead end.
Wow. Okay, listening to this. So DNS is essentially like an old printed phone book.
That's a good way to look at it.
Yeah, like it tells you where a business is located, but it doesn't know if that business burned down yesterday. If you call the number it gives you, it just rings endlessly.
Exactly. And the problem actually compounds when you try to fix it. Let's say you realize the server's dead, right? And you update your DNS records to point to a healthy server.
Okay, simple enough.
Well, the failover is agonizingly slow because of TTL time to live caching. Internet service providers and local web browsers physically cache those old DNS records.
Oh, I see.
Yeah, so even after you update the routing on your end, users across the globe might still be sent to that dead server for minutes or sometimes even hours until their local cache expires.
Oh, that's brutal.
And in a system with an 800 millisecond latency budget,
Yeah.
A 5-minute outage is just a catastrophic failure.
Yeah, so the printed phone book is definitely out. The notes say we need a load balancer, which, if we stick with the analogy, sounds more like a real-time, highly intelligent taxi dispatcher.
I like that, yeah.
Instead of just handing out numbers, this dispatcher is actively radioing all the cabs. Like, it knows exactly which ones are empty, which ones are stuck in traffic, and if a cab breaks down, the dispatcher instantly stops sending passengers to it.
That is exactly how it works. Under the hood, hardware and software load balancers are constantly sending health checks to your servers. They're basically pinging your instances every few seconds, asking, hey, are you still responsive?
And if they don't answer,
If an instance fails a health check, the load balancer just instantly removes it from the rotation and redirects traffic to the healthy instances.
that's so much smarter.
It is. And this active monitoring not only prevents dropped connections, but it actually allows for zero downtime maintenance. You can intentionally drain traffic away from a specific server, update its software, and bring it back online without a single user noticing the swap.
Hold on, though. If basic DNS is that blind and broken, why is it even in this architecture at all? I mean, why not just throw it out completely and use these smart load balancers right from step one?
What's fascinating here is how global server load balancing, or GSLB, bridges that exact gap. You physically cannot bypass DNS entirely because the fundamental architecture of the internet just requires it to translate your human-readable domain name into an IP address.
Right, you need that translation.
Right. But a GSLB, something like AWS Route 53 or GCP Cloud DNS, it functions as a highly intelligent DNS service. Instead of that blind round-robin guessing game we talked about, a GSLB evaluates several live metrics simultaneously.
What kind of metrics?
Well, it looks at the geographic location of the user, the current CPU load across your global data centers, the overall traffic volume, and the actual physical network response times. It does all this complex routing math in milliseconds to find the absolute best, closest data center for that specific user.
Wow, so if a user in Tokyo opens your AI app, the GSLB ensures they aren't routed across the planet to a data center in Frankfurt. It evaluates the network and points them directly to the Tokyo region. And then once they arrive at that specific regional data center, the notes mention a local layer 4, layer 7 cloud load balancer takes over to fan out the traffic to the specific microservices.
Yep, that's the next step.
I see those terms tossed around a lot, layer 4 and layer 7, but what is the actual physical difference for this architecture?
It really comes down to how deeply the load balancer looks at the traffic. A layer 4 load balancer operates at the transport layer. It's really just looking at IP addresses and port numbers.
So it's pretty basic.
Basic, but incredibly fast, because it's not reading the contents of the data packet. It's just forwarding it based on the address. A layer 7 load balancer, on the other hand, operates at the application layer. It actually opens up the HTTP request and looks inside.
Oh, so it can see what the user actually wants.
Exactly. It can see the specific URL path. So it says, oh, this user is trying to reach the gateway endpoint, and it routes the traffic based on that specific content. For a complex AI platform with multiple specialized microservices, you rely heavily on layer 7 to intelligently route requests to the correct internal systems.
Okay, so the GSLB got them to the right building in Tokyo, and the local layer 7 load balancer has directed them to the right door.
Yeah.
But you can't just leave that front door wide open and let external clients just wander through your internal microservices, right?
Absolutely not.
So how do you check their ID and secure the system without slowing them down and totally blowing past that 800 millisecond budget?
Well, this is where we implement the API gateway, which serves as the physical perimeter of your system. In a modern architecture, you split your application into dozens of specialized microservices, right?
Right.
So one handles billing, one handles speech to text, one handles user profiles. This is called API composition. But if you force a mobile app to keep track of all those individual IP addresses and talk to each service directly, you expose your entire internal organization to the public internet.
Which sounds incredibly dangerous.
It is. Furthermore, you'd have to build redundant security checks into every single one of those internal services.
Here's where it gets really interesting because the API gateway essentially acts like a strict nightclub bouncer.
Yeah, that's a perfect analogy.
It just stands at the single front door, checking IDs, making sure nobody's bringing in anything dangerous, and keeping a head count so the club doesn't get overcrowded. And because the bouncer does all that heavy lifting at the door, the bartenders, which are your internal microservices, they don't have to waste their time checking IDs. They can just focus purely on making the drinks.
Exactly. It provides consolidated security. The API gateway acts as a single choke point for authentication, authorization, and rate limiting. If a massive DDoS attack hits your system, the gateway recognizes the malicious traffic patterns and instantly drops those connections at the perimeter.
Protecting the fragile stuff inside.
Exactly, protecting your internal microservices from being completely overwhelmed. Once a request passes through the gateway, your internal services can safely assume it has been fully vetted.
But looking at the sandbox notes, there is a massive warning sign here about anti-patterns.
Oh, yes. Pay attention to those.
It explicitly says you must ensure multiple gateway instances run behind the load balancer so the gateway itself doesn't become a single point of failure. But the most emphasized warning is this: never put business logic in the gateway.
Never.
Which makes me wonder, I mean, if the traffic is already passing through the gateway anyway, isn't it incredibly tempting for a developer to just stick a little bit of audio processing logic in there? Like, why not have the gateway do a tiny bit of the computing work just to save a round trip to the back end?
I get why it's tempting, but doing that is a catastrophic trap for system scalability. If you blur the lines and start adding business logic to the gateway, you turn what should be a lightning-fast router into a massive computational bottleneck.
Oh, because it's pausing to think.
Yes, the gateway's only job is to manage the flow of traffic. The moment it starts trying to process data, it slows down. Requests start piling up at the door, and your 800 millisecond budget just evaporates. The gateway must remain emphatically, stubbornly dumb regarding your core application logic.
Okay, so what exactly is the gateway doing in this specific AI platform if it's not processing logic?
In your architecture, the gateway service has a highly specialized restricted role. First, it terminates TLS.
Meaning it handles the security certificates.
Well, more than just the certificates, it handles the intense mathematical lifting of cryptography. Setting up a secure HTTPS connection requires multiple back-and-forth handshakes to establish encryption keys, and that burns CPU cycle.
It takes actual processing power.
Exactly. By having the gateway handle all of that decryption at the perimeter, your internal microservices can communicate with each other over unencrypted, lightning-fast channels safely inside the network. Second, the gateway authenticates the user. And third, it rapidly upgrades that standard HTTP connection into a persistent WebSocket connection.
Right. The notes specifically highlight the WebSocket upgrade as just a critical step.
It is, because standard HTTP requires you to open a new connection, send a request, wait for a response, and then close the connection every single time you want to send a piece of data.
That sounds exhausting.
That overhead would just destroy a live conversation. A WebSocket, however, opens the connection once and keeps it wide open. It creates a persistent bidirectional pipe.
So the data just flows freely.
Yeah, the user can stream audio up, and the AI can stream audio down simultaneously without ever wasting milliseconds reestablishing a connection. Once that WebSocket is established, the gateway just cleanly passes the baton to your internal orchestrator layer.
Okay, so the user is safely past the bouncer. The secure, persistent WebSocket is open. Now the actual work begins. But here we hit a profound architectural conflict. An AI conversation requires two very different types of work to happen simultaneously.
Right, the fast and the slow.
Exactly. You have the lightning-fast, real-time audio processing, and then you have the slow, heavy background administrative tasks like logging analytics or calculating billing metrics. If we try to do both of those things at the same time, in the exact same way, the entire system is going to gridlock, isn't it?
It will completely crash. This introduces the fundamental difference between synchronous and asynchronous communication.
Okay, break that down for us.
Direct synchronous calls mean service A calls service B, and service A completely halts its own operations to wait for a response. It creates tight coupling. If you use synchronous calls for every action in your platform, you remove any buffer for traffic spikes.
Because they're all just waiting on each other.
Exactly. If 1,000 users suddenly log on, every single service is instantly hit with 1,000 requests, and they're all stuck waiting on each other to finish.
It's sort of like standing in line at a coffee shop and demanding your drink instantly. You place your order, and you stand there staring at the barista until the coffee is physically in your hand. Neither of you can do anything else until that specific transaction is complete.
That's synchronous, yes.
But asynchronous communication is like dropping off a huge catering order for tomorrow and just walking away. You hand over the request, and the kitchen deals with it at their own pace while you go about your day. And the notes emphasize using message brokers to handle this asynchronous work.
Yeah, a message broker essentially places a queue, like a literal waiting room,
Uh,
between the sender and the receiver. And under the hood, that waiting room is often backed by high-speed disk drives. The benefits for system stability are just immense.
How
First, buffering and scaling. Brokers absorb massive traffic spikes. If a viral moment hits and traffic spikes 100-fold, your back-end database isn't overwhelmed. The broker just catches all the incoming messages, holds them safely in the queue, and allows the consuming database to drain them at a steady, manageable pace.
Wow. And it provides serious fault tolerance too, right?
Oh, unmatched fault tolerance.
Mm.
If your analytics database suddenly crashes and goes offline, the system doesn't break. The message broker simply writes the catering orders to its internal disk and holds them there safely.
So it just waits.
Right. When the analytics database reboots and comes back online hours later, it just picks up right where it left off. You suffer zero data loss. It also enables pub/sub routing, publish, subscribe.
What does that mean in practice?
A single event, like a user finishing a sentence, can be published to the broker once, and the broker instantly fans it out to the billing service, the notification service, and the analytics service simultaneously, without the core audio service having to talk to any of them directly.
Okay, but if message brokers are this incredible, preventing crashes, absorbing massive spikes, guaranteeing no data loss, why don't we just use them for absolutely every microservice in the platform? Like, why not put a queue between everything to make the system totally indestructible?
Well, if we connect this to the bigger picture, your 800 millisecond constraint, you realize you cannot put a queue between everything. Queues, by definition, introduce overhead. They introduce wait times.
Oh, right, the waiting room.
Exactly. If you place a message broker in the critical path of the live audio processing, you will blow past 800 milliseconds before the AI even formulates a thought. The live conversational loop cannot afford to wait in the line.
Ah, so the AI and the user have to remain at the coffee shop counter demanding instant service.
Precisely. In your sandbox, the live loop, which is the orchestrator communicating with the screamer, the speech-to-text service, that pathway must remain completely synchronous via gRPC.
Wait, why gRPC specifically instead of standard REST APIs?
Standard REST APIs typically rely on JSON, which is very text-heavy. It takes time for the server to parse all those readable text characters. gRPC, however, uses protocol buffers. It compresses the data down into a very dense binary format.
So that's much smaller.
Much smaller and much faster. It transmits bare metal ones and zeros over the HTTP2 protocol, which means it can actually multiplex multiple requests over a single connection simultaneously. You are saving precious milliseconds by stripping away all the bulky text formatting. It provides a direct, instantaneous connection.
But the off-path tasks, the billing and logging, they still need to happen.
Right, but they cannot be allowed to jeopardize that live connection. Every time an audio turn completes, the orchestrator needs to trigger billing and analytics. But it can't afford to halt the live AI conversation to wait for a slow database to acknowledge the record.
So what does it do?
It just fires the data off into an asynchronous Kafka-style event stream or an SQS queue and immediately turns its attention back to listening to the user. By decoupling the background tasks, you guarantee that a slow billing database will never, ever stall the live AI chat.
Okay, so we've engineered a pretty brilliant back-end data flow. We have GSLB routing traffic to the nearest continent, an API gateway securing the perimeter and upgrading to WebSockets, and this beautiful split between ultra-fast synchronous gRPC for the live audio and asynchronous Kafka queues catching the heavy background tasks.
But is bulletproof.
It sounds bulletproof,
Yeah.
but if the front-end interface, like the actual web console where your users log in to configure their AI agents, type in prompts, and adjust their dashboard settings, if that static website takes 3 seconds to load, the whole platform will just feel incredibly slow to the user.
That's a huge problem.
Yeah, it completely ruins the illusion of speed we just worked so hard to build on the back end.
And that's because the user's perception of system performance is heavily dictated by the absolute slowest component they interact with. And this brings us to the Content Delivery Network, or CDN.
Right.
A CDN is a globally distributed network of proxy servers specifically designed to cache static assets. We're talking about HTML layout files, JavaScript bundles, CSS style sheets, images, and fonts. It caches these files on edge servers at points of presence, or POPs, that are physically located as close to the end user as possible.
And the latency math here is what really drives this home. Let's say your primary data center is located in Virginia,
Yeah.
right? And a user sitting in Sydney, Australia opens your web console. If their browser has to fetch all the heavy styling and layout files all the way from Virginia, the physical round trip across the Pacific Ocean just takes forever. You're looking at maybe a 3,200 millisecond load time just to see the login screen.
Which is unacceptable.
Totally. But if those exact same files are cached on a CDN edge server right there in a Sydney data center, the load time drops to under 800 milliseconds.
You are quite literally bending the rules of geography. By skipping that long-haul trip across the ocean, you dramatically reduce latency. And there are two main strategies for managing how those files get to the edge servers: pull and push.
How does pull work?
In a pull strategy, the CDN waits until a user in Sydney actually requests a file. If the Sydney edge server doesn't have it, it reaches back to your origin server in Virginia, pulls it down, delivers it to the user, and then caches it locally based on a time-to-live setting so the next Sydney user gets it instantly.
Got it. And push.
In a push strategy, whenever your engineers update the code, your deployment pipeline proactively pushes the new assets directly out to all the global CDN edge servers simultaneously before anyone even asks for them.
So what does this all mean for your specific sandbox? A CDN is essentially like having a local corner store that stocks your favorite brand of milk. Instead of making you drive all the way out to the main dairy farm 50 miles away every single morning, the corner store just keeps a fresh supply right down your street. It's infinitely faster for you, and it stops the main dairy farm from being completely overwhelmed by thousands of individual people showing up at dawn.
That's the perfect way to visualize it.
But for your AI platform, we have to draw a hard line between what goes to the corner store and what actually requires a trip to the farm.
This raises an important question. How do we handle the incredibly dynamic bidirectional WebSocket streams carrying the actual AI conversational audio? The answer is we don't cache them at all.
They just bypass the CDN entirely.
Entirely. A live audio stream physically cannot be cached because it is completely unique, context-dependent, and happening in real time. But the static web console itself, the user interface, the buttons, the JavaScript that renders the dashboard, that absolutely should be fronted by a CDN in pull mode.
Right, because the visual dashboard looks exactly the same for a user in Sydney as it does for a user in London, until they actually log in and start talking.
Exactly. By utilizing the CDN for those static assets, you offload a massive amount of repetitive, heavy traffic from your primary servers. Your backend doesn't have to waste precious CPU cycles serving CSS files. It can dedicate 100% of its compute power to processing the complex, demanding AI WebSocket streams.
It's such a smart divide.
It really is. This hybrid approach keeps the front end feeling incredibly snappy on a global scale, while fiercely protecting your backend power for the deep conversational logic.
It is truly brilliant architecture. So to recap this incredible journey through your engineering notes, we started by using global server load balancing to intelligently evaluate network latency in milliseconds, routing every single user to the absolute closest, healthiest data center, completely abandoning the blind guesswork of basic DNS.
Yep, solving the routing problem.
Then we set up a highly restricted API gateway to act as our perimeter bouncer, securing the system, performing the heavy mathematical lifting of TLS termination, and immediately upgrading connections to persistent WebSockets without ever processing business logic.
Exactly right.
From there, we physically split the processing pathways. We instituted strict synchronous gRPC connections utilizing compressed protocol buffers for the live AI audio to guarantee we stay under that 800 millisecond budget.
Protecting the conversation.
And simultaneously, we offloaded all the administrative logging and billing to asynchronous message brokers backed by high-speed disk drives, preventing back-end database stalls from ever impacting the live conversation.
Handling the background tasks flawlessly.
And finally, we wrapped the entire static front-end dashboard in a pull mode CDN, ensuring the platform feels instantly responsive no matter where on the globe your user happens to be sitting. Together, these physical building blocks take the abstract concepts on your whiteboard and guarantee your non-negotiable latency constraint in the real world.
It's an incredibly solid foundation.
It really is. But before we wrap up, you are building an architecture perfectly designed to decouple the heavy physical infrastructure from the intelligent AI itself. Everything is built to let the AI just focus entirely on talking. But looking toward the future, I want to leave you with this.
Oh, this is a fun thought.
What happens when your AI agents become intelligent enough to actively monitor their own underlying system loads? Imagine a future, maybe not so far off, honestly, where the conversational AI can actually feel the traffic spiking across the network and dynamically reconfigure its own message brokers, or automatically spin up new API gateways in real time completely autonomously based on how emotionally intense or computationally heavy a massive global conversation is getting.
That would change everything.
Right. The physical architecture wouldn't just host the AI, it would be actively driven by it.
Fascinating stuff to think about.
Truly. Well, thank you so much for sharing your highly technical sandbox notes with us today for this deep dive. Best of luck with the global deployment of your platform. Keep building, keep protecting those 800 milliseconds, and keep learning.